Hi, it's multimeter review time again. In this video, we will take a look at this Holtpeak HP770D 40,000 counts true RMS multimeter. I requested this meter from Banggood for a review. If you're interested in this meter after watching this video, please check out the product link in the video description below. Now, this is actually not a new design. This meter has been around for quite a few years now. One of the reasons got me excited about this meter is its input jack design. If you take a closer look, you will see that the input jacks are protected by these shutters. They only allow you to plug in the leads into the sockets that are appropriate for the current range you are in. And if you already have leads plugged in, you won't be able to switch to a different range that could potentially damage your meter. You can see this mechanism in action when I cycle through the ranges. Now, for instance, I'm in the current range, and you can see that the only jacks allow you to plug in is this current range jack. And similarly, if I'm in the amp range, you can only plug into the amp range. So that is quite neat. To me, this is a very clever design, and in my opinion, this design is superior to other designs I have seen, as it physically prevents you from switching into the wrong range. For example, right now I have it all the way on the current measurement side, and if I plug in the leads into the 20 amp sockets here, the only range I can switch to is this amp range, and cannot physically change it to any other incorrect range. This prevents some common absent-minded mistakes that could potentially damage your meter and endanger the operator. One of my first digital multimeters, which is a Craftsman branded manual ranging multimeter, also had this feature, and I loved it. I'm glad to see that this protection mechanism is still being used in this more modern auto ranging multimeter here. Another reason I wanted to take a look at this HP770D is that this is a 40,000 counts meter, which is an improvement over the 22,000 counts Unity UT61E Plus that I reviewed a while ago. The reason I'm comparing it to the UT61E Plus is that these two meters are about the same price. And if you take a look at the specs that is included for this HP770D, you will see that it is pretty impressive in terms of its capabilities. One thing jumps out is the 40 millivolts range for both the AC and DC measurement. In these ranges, you can see that the voltage resolution comes in at 1 microvolt, which is much better than the UT61E. For that meter, it only has a resolution down to 10 microvolts in its millivolt range. Of course, we will have to test it shortly to see if it actually capable of achieving this level of resolution. One thing you'll immediately notice is the placement of the common jack. It is all the way to the right, which is different from most of the multimeters. If you see this Unity UT61E, for example, the common jack is actually the second one from the right. The reason is because of this shutter design, as it has to cover these 3 consecutive jacks. If you have the common jack in the middle here, it will make the mechanism very complex, if not impossible. So if you take a look at our Craftsman meter that I mentioned earlier, you will see a similar design that the common jack is all the way to the right. The arrangement of the ranges is also a little bit odd, as the voltage measurement starts from the right-hand side, which is opposite from pretty much all the auto-ranging meters I have used. So it does take some getting used to, but I don't think that's a big deal at all. The meter comes in a soft pouch, and it also has a thermocouple, as the meter is capable of measuring temperature. Okay, without further ado, let's take a closer look. Now let me power it down. You will notice that the display is very crisp and the contrast is excellent under most of viewing angles. One unique feature is the automatic backlight. You can see a photoresistor right here for ambient light detection, and notice if I block it, the backlight will come on automatically. I think this is a very neat design, and I'd like to see wider adoption. The range switch itself feels okay. It is a little bit light in my opinion, but it is nevertheless very precise, and to be very honest, it is better than most of the meters I have used. Now, especially comparing to the UT61E I mentioned earlier, I did not quite like the range switch design on this UT61E, but this meter feels just about right. And now I have hooked it up with the DC voltage reference. And a lot of folks ask me what the DC voltage reference I'm using, and it is an Electronic Development Corporation EDC MV216A. And right now we're in the volt range, so for this test we're going to increment the voltage 1 volt at a time, so just to save some time. So let's start with 1 volt. And you can see it's pretty much bang on. By the way, the accuracy of this meter is stated for the volt range is roughly 0.1% plus 2 counts. So that you can see it is roughly in line with what the spec says. So now let's go to 2 volts. No problem. 3 volts. 4 volts. And because this is a 40,000 count meter, if I increase it to 5 volts, I'd expect we will lose 1 digit here. So let's go to 5 volts. Yep. And 6 volts. 7. 8. 9. 10. No problem at all. Now let's test the millivolt range. I have already changed my voltage reference to output millivolt instead of the volt range. Now, the millivolt range is spec'd at plus minus 0.5% plus 5 digits accuracy. So you can see that at 0 volt output, we do see some residual voltage here. Now, that is not necessarily the problem from this meter. It could be the output from my EDC voltage reference. So let's first route it out so that we can start clean. So now let me dial up the voltage and we'll see what we observe on this meter. So now let's do 1 microvolt. Because we're actually incremented 1 microvolt at a time, and for this kind of extreme low voltage measurement, there's going to be some fluctuation. So you might want to make sure that you give it enough time for voltage reading to settle before you take a new measurement. So let me increment it to 2 microvolts, 3, and you can see that the last significant digit is actually roughly in line with what we dialed in currently on the voltage reference. Now 4, 5, 6, that is actually very impressive. 7. If you recall, in our earlier testing of the Onon A70, that meter was not able to discern the last significant digit, even though it can display down to 1 microvolt range, but it cannot do that measurement. The only measurement it can do is roughly at 10 microvolts. So 8, 9. So now I'm going to do 10 microvolts, 20, 30, 40, 50, 60, 70, 80, 90. No problem at all. Let me just do the millivolt. Let's do 1 millivolt, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as you can see, the low voltage measurement of this meter is actually very, very impressive. One thing I forgot to mention is that this meter is advertised as a Cat 3 1000 volt meter. The supplied leads also seem to agree with the Cat rating. As you can see here, it's Cat 3 and 1000 volts. We will have to take a look when we do the teardown later to get a sense whether or not this Cat 3 rating is appropriate. Another thing I forgot to mention is that this meter also comes with a bar graph display, as you probably have seen in my previous test. That display is located in the upper half of the display, so that makes it very easy to see. But one thing I did notice is that the update rate of that bar graph is not as fast as I'd like it to be. and usually you want it to be much faster than your display so you can actually see the signal variation, but it appears that the bar graph updates at about the same rate as the display itself. Now, to take a look at that bar graph update rate a little bit more clearly, I hooked up a UTG-962E. Currently, I'm outputting a square wave signal from 0 volts to 2 volts at roughly half hertz. So you can see that we are ramping up and ramping down. Clearly, there is some delay in that bar graph because this is a square wave. So ideally, you should see that jumping straightly to the halfway mark and going down as rapidly as it rises up, but it's not doing that. So that makes me believe that the update rate is not as fast as it should be. And let me just increase the waveform frequency. Now it's to 1 Hertz. And we're still able to see that on a bar graph. So let me increase it to 2 Hertz. And you can see that we already are not quite able to keep up with the pace. So if I increase it a little bit more to 3 Hertz, 4 Hertz, 5 Hertz, you can see that this bar graph becomes pretty much useless now. So this is actually one of the shortcomings of this meter. So with the slow updating rate of the bar graph, it is not as useful as it could be with a faster update rate. But nevertheless, you do get the sense of where the current measured signal is with respect to the whole range. And by the way, within any of the measurement range, you can always use the range button to manually set the range instead of doing the auto range by the meter itself. Just wanted to point that out. And next, let's take a look at the AC measurement performance of the HP770D. For that, I also hooked up a Unity UT61E Plus so that we can do some comparison and you can see the update rate and also the measurement accuracy between these two meters. So now let me dial up the Variac. You will see that their readings largely agree with each other. And the update speed of the 770D actually is pretty fast. You can see that. And so that's great. Now let me dial it up to the maximum. I can adjust. Now I'm at the maximum output of the Variac, and you can see that the measured voltage readings are largely in line with each other. Now let's move on to the ohm measurement range. First, I want to see how fast this range is. For that, I'm going to short the leads, and you can see that it's actually not that great. I mean, it's definitely adequate. I think it's roughly the same speed as the Aneng AN-A70 we reviewed previously. First, I want to measure a 100 ohm 0.1% precision resistor, and for that, I'm going to route out the leads first. Now, keep in mind, these are not gold-plated leads, so it could be a little bit tricky to precisely route out the residual reading here. So let's route it out. And now let's measure the resistance here. And the reading is 99.68, and it's a little bit lower than the actual reading, but if you read the spec for the meter, the ohm range here is spec'd at 1% plus minus 10 digits, so that definitely is still well within spec. Next up, we'll try a 1 mega ohm resistor. So let's see how fast we can measure it. Not bad. Certainly not bad at all. Next, on to diode measurement mode. And I'm just going to test a couple of LEDs. First one I'm going to test is a red LED. Let me see if we can see it light up. Yeah, it's very faint, but it does light up. And its forward voltage is at 1.6 volts. Now, the output voltage for the diode measurement is at 2.7, so it should be able to light up a white LED as well. So let's see that. This is a white LED. And yeah, it does light up, but it's not able to show the forward voltage drop. Now the continuity mode. And there is a little bit of a delay, as you can see that, but the delay is nevertheless very slight. So it's actually not that bad, but it's nevertheless not instantaneous as some other meters we have tested. Now on to the capacitance measurement. Now I am a little bit disappointed in the capacitance mode as you cannot use it to measure capacitors in the picofarad range, as the resolution in that range is only at 10 picofarad. And this is quite a pity as most of the meters I have used all have a resolution down to 1 picofarad. So to demonstrate that, I'm going to route out the reading, and you can see that already we have only at the 10 picofarad range here. This is the lowest it goes. So for example, if I'm trying to measure this 22 picofarad capacitor, I'm not able to do that very precisely, as you can see here. So that's definitely a limitation. Now let's measure a 100 nanofarad capacitor, and for that we should not have any problem. By the way, this capacitor we measured earlier with other meters, the value is actually a little bit low. I think it's around 75 nanofarad, so we'll see. And the speed is certainly not that fast. Yep, it's reading 74.5 nanofarad, so no problem at all. And next, I think I will measure a larger capacitance capacitor. This one is a 3,300 microfarad capacitor. So let's take a look. Again, the measurement is very slow, but as you can see, that is settled at 3 millifarads. So that's definitely within the accuracy range. The largest capacitance can be measured by this meter is spec'd at 99 millifarads. Now let's take a look at the frequency measurement capability of this 770D. And for that, I hooked up a UTG 962E signal generator at the input. Currently, it's outputting a 1 Hz, 1 volt RMS sinusoidal signal. And you can see that the meter here displays the 1 Hz signal without any problem. And according to the spec, it can measure signal up to 10 megahertz. So let me increase the frequency, and we'll see at what point we are not able to measure the signal anymore. Now we're at 10 hertz, no problem. 100 hertz, no problem. 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz. And let's start 1 megahertz at a time. 2, 3. Keep in mind that the range may depend on the signal voltage, but for this testing, we're just going to fix it at 1 volt RMS. 4 meg, 5 meg, 6, 7, 8, 9, 10. No problem at 10 megahertz, so let's increase beyond that. 11, 12, 13, 14, 15, still no problem. 16, 17, 18, 19, 20. It seems that 19 megahertz is the highest we can go. What's interesting is that when we reach the 20 megahertz, it actually goes haywire instead of gradually losing the ability to track that input signal. So not entirely sure whether or not there's some hardware limitation on the counter side that prevents it from detecting any higher frequencies. Right now we're at 19 megahertz. There's no problem. By the way, the frequency measurement, you can also use that to measure duty cycle. Of course, right now it's a sinusoidal, so you would expect that it's around 50%. But that's the capability of this meter here. Now let's take a look at the non-contact voltage detection here. And I'm going to use this power strip to illustrate. And you can see that it's actually very sensitive. As we move closer, you will see that it started beeping faster and faster. So that clearly is very sensitive here. And one biggest problem of the non-contact voltage detection is that the sensitivity sometimes is very tricky. When it's too sensitive, it is going to trigger a lot of false positive. For example, this one, in my opinion, is very, very sensitive. If I tap the top you can see that it triggers that non-contact voltage detection. So clearly that is not good if you're trying to definitively tell whether or not a wire is live. Now, on the other hand, some meters, for example, the UT61E Plus we tested a while ago, the sensitivity is extremely low. You really have to squeeze the wire right next to the sensor in order to trigger the alarm. That's why I personally don't use the non-contact voltage detection on these kind of multimeters. Now let's take a look at the temperature measurement range. For that, I have to unplug the leads because the shutter is preventing it from changing to the temperature range. I won't be plugging in the thermocouple here, but you can see we do have some advantage on this meter as the temperature range has a 0.1 degree resolution versus the 1 degree on most of the meters that I have seen. So we can also change it to display Fahrenheit versus Celsius. This meter can also measure transistors HFE. Now, the inclusion of HFE measurement is always somewhat controversial. Some folks won't even consider a meter professional grade if it includes the HFE measurement. I don't see what the big deal is, as it does have its appeal to many hobbyists, myself included. If you do not need it, you can simply just ignore it. That said, if you do intend to do serious electrician work and use meters in Cat 3 or Cat 4 setting, you probably want to get a reputable brand multimeter anyway. Most of the hobbyist work is Cat 2 rated, and having a transistor socket on the meter is perfectly fine, safety-wise. And while we're in this range, let's just measure a NPN 3904 transistor and take a quick look here. These kind of sockets are not as good as the dedicated sockets provided by Unity UT61E, like the one I showed earlier. Now this is a little bit tricky to get good contact, but once you get a good contact, you can see that we can measure the HFE with no problem. Now let's take a look at the current measurement. First, let's take a look at the microamp range. The accuracy, according to spec, is rated at 1%. So now let's take a look at my 100 microamp current standard, and let's see what the current reading is. It is at 99.84, no problem. There is another benefit when using a higher count multimeter like this one, especially when doing current measurement. This is due to the burden voltage. Depending on design, the full range voltage drop is between 0.5 to 1 volts, depending on the specific meter you use. Sometimes this burden voltage can become quite problematic if your circuit is sensitive to voltage changes. With a high count multimeter like this one, you can use a higher range to measure the current while still get a reasonable resolution. For instance, to measure a circuit with current consumption up to a few hundred milliamps, you can use the amp range on this meter, and it will still give you a 0.1 milliamp resolution. The obvious benefit is that you get very little voltage drop. So let me demonstrate that next. In this setup, we're outputting a 200 milliamp current from my HP6181C DC current source. The 200 milliamp current is currently being measured by the HP770D. You can see that we're currently in the amp range, and the input is into its 20 amp input jack. With this setup, you can see that the burden voltage is at roughly 70 millivolts, and we still have the 0.1 amp resolution on the current reading. And now if I switch to the milliamp measurement range, you'll see that the voltage drop is going to be a little bit more significant here. So let me plug that in. Of course, the benefit is you get more current resolution, you get one extra digit. But the voltage drop here now is at 0.4 volts. So clearly you see the benefit of using a higher range when measuring your current reading. So what I demonstrated here is that if you don't need that extra digit of resolution, you can simply use a higher current range to do the same measurement, and you will get a much lower burden voltage. Now, before I open up this meter, let's take a look at its current consumption. Unlike a lot of recent meters only using AA or AAA batteries, this meter does use a more traditional 9-volt battery. Now, a lot of people don't like this arrangement, but in my opinion, as long as the current consumption is reasonable, a 9-volt battery should not be a problem. So let's take a look at how much is the battery consumption here. And by the way, I already turned on the meter, so let's just put the leads on here. And it's only drawing about 5.6 milliamps. So that's actually not that bad at all. And this one battery can last you for a long time, for sure. I just removed the back cover from the multimeter, and you can see the circuit board inside now. The back cover is actually only secured by these 2 screws here, and there were some clips on the front to clip it on. One thing disappointing to see is that we don't have any MOVs on the front end, at least not on this side. I doubt it is on the other side, but later on we will probably take it off and just to verify. Anyway, there's only a single PTC here, so that clearly is not going to meet the Cat3 rating, as there's no MOV to absorb any kind of a transient. This is the input current shunt that is for the 20 amp current measurement range. You can see that the input jacks are actually secured onto the input via these 4 screws, and there's a shake-proof washer in between. That is definitely nice attention to detail here. By the look of the 2 fuses included on this PCB, they're most certainly not HRC fuses. And there's no barriers between the fuses and the rest of the circuitry, so in the event one of the fuses ruptures, it is very likely that it would damage part of the circuit board. And also, I don't see any high voltage cutouts on the PCB either. And these features I just mentioned, such as the high voltage cutouts, the blast shield, and also the MOVs, are almost always found in a properly designed Cat3 rated multimeter, but obviously they are absent in this one. With that said, you can definitely use this meter with no problem to measure low energy circuitry, for example, your everyday electronics work, and that should not be any issue at all. Towards the middle here, you will see an LED. I actually forgot to mention that earlier when I was demonstrating the backlight, but you will see here on the other side, the LED comes through this light pipe and comes out from the tip of the range switch. So when the backlight is on, the LED actually illuminates the range you are currently in. So that is a very clever design in my opinion. Up here we have a 3-pin chip that is a 7530-1 3 volts linear regulator. So in theory, this means that the circuit can operate all the way down to just above 3 volts. On this side you can see a few more chips. The smaller one is a HY3131, which is a multimeter front-end chip capable of supporting a 50,000 count design. This larger chip here is an HY11P14, which is a mixed signal controller, and it includes a LCD driver and an 18-bit ADC. This 8-pin chip here is a 2402A, which is an EEPROM that is used to presumably store some calibration constants for the multimeter here. Interestingly, you can see we have an empty footprint for a resistor network. So you can either use a precision resistor network as shown here, or you can use these individual resistors as how it is currently implemented. And by the look of it, this looks like a programming header that is used for programming the mixed signal controller. Up here we do see a trim pot, not entirely sure what that trim pot is adjusting. And also you can see we have an antenna for the non-contact voltage detection here. For completeness, I took this board out entirely, and as we expected earlier, there's no MOVs to be found on this side of the board either. And let me remove this switch carefully so I can just show you the light pipe that I mentioned earlier. So you can see that LED sticks out from the side and it goes in here through a light pipe, and you can probably see if I position the angle a little bit better, and you can just about to see that light comes out from this tip, so that illuminates the dial when the backlight is on, as I mentioned earlier. So let me put this back. And on this side you can see the shutter mechanism. The shutter moves back and forth, and that is driven by the grooves on this range switch. Overall, I'd say it is a pretty decent 40,000 counts meter. Now, I hope you enjoyed the video. If you liked the video, please remember to give it a big thumbs up and remember to subscribe and share. I will catch up with you next time.